Hi, this is Tavi Greiner, Astronomy.FM's Vice President of Communications. If you enjoy our programming, please let us know with a donation to Astronomy.FM/donate. We really do rely on your support, and it's true, every little bit counts.
AFM.
Program complete. Enter when ready.
The curtain of night is drawn back. The telescopes are trained. The domes are open. The audience is set. Now, step into the event horizon.
Good evening, everyone, and welcome to the Event Horizon here on Astronomy.FM radio. It is another Friday evening, 9 o'clock in the evening on February the 2nd, 2018, for those of us here in the eastern portion of North America, and Universal Time, that would put it at 2 o'clock in the morning, Saturday morning, February the 3rd, 2018. My name is Marty Kunz with my co-host, somebody different tonight,
John Foote.
All right, John, glad to have you here.
Glad to be here.
Nick is out. A little dental work. You can't talk. So it's me and John for the next couple of weeks. He'll be here. John will be here next Friday too. So we will go on. Got a little different thing with our chat room. We've updated our chat room. The address is slightly different now. So you would go to chat.astronomy.fm. That's different than what it used to be. So, or you can still go to the homepage and look where it says Radio Chat. Click on that too, and then just type in a name and then hit login, and you'll be here in our chat room where we post links to things that we're talking about. You can talk to us if you want to. Type in stuff in the chat. Come on out. And
if you see like the front page, when you log in for chat, it'll show you your username. It'll ask you for a password and all that stuff. Don't worry about the password. Just put a username in. Just put username in, hit enter.
That's right. Yep, that's all you need. No password.
Don't worry about the rest of the...
Don't have to sign up. Yep.
No.
Name,
it's just a temporary login page for the evening.
Yep, that's it. So come on over. Glad to have you here. And if you're new to chat, type in where you're listening in from. It's always kind of fun to know where people are from. Get people from all around the world. And, of course, we will repeat this program every 4 hours for the next 24 hours. The chat room's always open, but generally only during the live portion, like right now, is when most people come out to the chat. And that's the best time to get a hold of us, too. So, all right, let's see. Where do we want to start out?
Well, it's been a busy week.
It has been a busy week.
Got to talk with the moon. Oh, we got to talk about it. We got to say hello to it.
We can talk about it. Yes,
it was good. It was a good adventure, but I had an extra benefit.
Okay.
The extra benefit for me was it was my birthday. So yeah, I really enjoyed the moon that night. For what I can get to take a look, and really enjoyed FM that night too. The Pirates was a great evening. Oh, remember we were at for Pirates.
Oh, okay.
It was during Pirates. Yeah.
Yep. The eclipse actually occurred Wednesday morning for those of us for where I'm at, east side.
I had to watch it online. But that was good.
Did watch? You got up and early watched? Yeah, I couldn't even see it live because it would have been partially visible. I've done this before. Usually when I live a little farther north of here, about 50 miles or so, I had this big field I could go into, and I could see pretty reasonably down to the western horizon. So if I did that, I would have been able to catch this one, but early in the morning before the sun rises, I just didn't feel like doing it this time. And somebody else went out and looked, and they said it was cloudy here in Michigan anyways. So no big deal. So I've seen them before.
I'm in Atlantic Canada, so we're on the other side of where it was happening. Yeah.
Yeah, you're farther east than me.
Yeah.
By a big shot there. So
it was nice. Big shot. Oh, I like that. No, just a little mirror timer. Thank you for the birthday wishes, guys, in the chat room. Glenn, good evening. I don't know how to pronounce that. Is that Believe, Marty?
Yes, it is Believe.
Welcome, Believe.
Me, Glenn, got Nick in here. You, of course, Believe, and Evil Spock.
And some numbers coming in. Hey, numbers.
Yep. Glad to have you.
Just hit enter. Just hit enter. Hit that page. You're not sure what to write is. Don't want to put a name. Just hit enter.
That's true. Yeah, you don't have to have your real name either. So most people don't. Just make up a nickname.
You're welcome to come in. Welcome.
Yep. No. See, Nick always makes up a nickname.
Yeah.
Now he gets it.
Not going there. They're interesting. They're usually characters from some 1950s British sci-fi, 60s.
Anything's fun. About the only action we have was as far as the moon and planets go this week is pretty much, it was yesterday, and that was it. The moon and Regulus were really close together for most of the world, but some places got an occultation. I think that was actually, is that down in, I don't remember where that was at. Oh, well, pretty far out. No, where it was really cold. It might have been like Antarctica.
Oh.
Kind of like next Friday. The moon is going to go in front of the asteroid Vesta, but again, that's going to be like from Antarctica, outrageously far south right now, so that's no good. Well, next Wednesday, we've got the moon's going to start getting last quarter, and it's going to start getting down towards the Scorpius region where all the planets are right now. So we'll have next Wednesday, the moon will be 4 degrees south of Jupiter. No, sorry, Jupiter will be 4 degrees south of the moon. Next Friday, Mars will be 4 degrees south of the moon. And again, Vesta is going to go behind. The moon's going to go in front of Vesta next Friday also.
Going to be a lot of people trying to measure something?
I don't know. It's just kind of using it as good marker to figure out what planet is where. If you know when the moon's going to be really near a planet, and if you don't know that's actually a planet, so when we give the reports that the moon's going to be near a planet, you just have to go out that night, look for the moon, and figure out, okay, the next brightest star in that area is probably the planet that I talked about. Yeah. Got an official lunar occultation of a star coming up next week, February the 8th. Not a really bright star. It's I think it's Gamma Libra, which is just west of Scorpius. So the moon's going to go in front of that star, but it's going to happen around Europe, Middle East, and Western Asia will be the only parts of the world that'll be able to see this. And then back around around the end of February, like we had last month in January, around the end of February, the moon's going to go through Taurus quite a bit and go in front of a bunch of those stars there. So probably like a bunch of the Hyades stars. It is going to go in front of Alpha Taurus, which is Aldebaran. Yes. So that'll be in a few more weeks, so around February the 23rd. So it's kind of happening a little bit regularly now. So the moon gets right through Taurus there. It's the way the ecliptic's kind of lined up. So let me put that link. Let me put that link into our chat room. Because it's one that I reference kind of regularly, and you can read it. It gives you a whole year's worth of what the moon is going to go in front of. And as far as stars go, they're going to be fourth magnitude or brighter. And it'll also say the area, what part of the world you can actually see it from. So you can't see it from all over the world, but only certain regions. And there's that link in our chat room there, too. We'll get that link into our Facebook page, too. So when you're listening and repeat, you can go to the Astronomy.FM, the Astronomy.FM, Facebook page. And I don't remember if it goes into our homepage or not. Maybe. And you can kind of look at the link and see what I'm talking about there, too. Oh, and here's the other one, too. This is from the U.S. Naval Observatory. Let me put that in. That's one that tells what's happening with the moon and planets, and when there's going to be occultations or when they're close to each other, stuff like that. 2 references I use regularly every week. And again, I want to remind you to our chat room address has changed. It's now chat.astronomy.fm. That'll get you there. Or you can go to the homepage, look where it says radio chat. Either way, it will get you here. Let's see. Got a launch coming up here next week, February the 11th. Progress cargo craft is going to launch to the International Space Station.
Taking cargo, I take it.
Mm-hmm. Okay. Yep. Let's see. Progress is, which one? What does Progress grow up on?
It's a vehicle. I'm not sure.
Okay. I've lost track of all the rockets and capsules and missions and stuff like that.
Well, at least you didn't lose track of a satellite and have an amateur find it for you.
Well,
that was pretty cool find.
Well, there was.
And we're referencing the amateur astronomer who discovered that long-lost mass satellite?
It was called Image.
Image,
yes. It's the one that an amateur radio astronomer, he likes listening to the radio signal from satellites and being able to identify which satellite he's actually listening to, and he does that with radio waves. Some people look at satellites with their telescope and try to identify them. That's fun too. He did this with radio waves. He was looking for the one,
the new one
that launched, and got lost, or potentially got lost. It was a spy mission. Mm-hmm. It launched, and then they said that they couldn't find it anymore once it got up there. Not too sure if that was supposed to do that or not, but anyways, he was looking for that one and came across another satellite, and he identified its position and found it was a NASA satellite that has been not broadcasting for 8-10 years, something like that. I think it was launched in 2000, lost in 2005. And he was able to identify it, and now it's like, oh, we could start using the satellite again.
Yeah, it's feeding back.
Yep. Here's an article.
I heard the spy satellite. Last time I heard it had a real nice view of the Indian Ocean. The floor, anyway.
Oh, really?
Yeah, having a really good view of the floor of the Indian Ocean somewhere. It's top secret exactly where it's looking at the floor. Because it's on the floor, I guess, yeah.
Is that what the latest they think, that it actually did not make orbit?
I don't know.
Don't know.
And please don't come and take me away to find out, because I don't know. I'm just another idiot in the radio making stuff up. Last I heard, something happened. They turned it around and put it in the drink. People have looked for it. This guy was looking for it too. It's not where it was posted.
Mm-hmm.
It originally had been certified some numbers, said it was in orbit, as if it was in orbit, and then they cleared it. And in order to clear it, you would have to turn it around and put it straight down into the Indian Ocean.
Oh, you point it into the ocean?
Yep, pointed it and sent it back down in the Indian Ocean. Something wasn't working.
Oh, I see. They would crash it.
Now, how can you get a satellite out of orbit that fast? So it was during launch, something happened, and so they just pointed it down. It never got up. Yeah.
Oh, okay. So you think it was a miscommunication in the thing, is what you're saying? Or it did something wrong, so they brought it back down on purpose?
They just brought it down on purpose. It wasn't working. In order to put it into the Indian Ocean, if it did go in there, they would have literally had to turn it around in flight and point it straight down.
Gotcha. Well,
and to do that would mean there was something majorly wrong.
Okay. Well, you don't actually point a satellite straight down when you want to get rid of it.
Not when he's trying to fly it straight up.
Yeah, well, I guess that's true. Well, you're still going to get some orbital speed on the thing. Generally, spy satellites are north-south launch trajectories, not east-west so much. So a little bit, not directly north-south, but generally going over the poles and let the Earth basically just turn under it, and that way they could see pretty much every part of the entire Earth, the North Pole, the South Pole, and the Earth rotates around it, so it doesn't have to go into orbit equatorially or even at an angle. The space station goes at an angle, I think it was about 54 degrees, something like that, so it covers a fairly large majority of the surface of the Earth. Just doesn't quite go over the poles.
No.
But it's pretty high. And there's some of them that, like the Hubble Space Telescope, that's pretty much like right on the celestial equator. And that's one reason, like you and me, we can't see it from here. We're too far north. We can't see over the horizon.
The stars are always brighter on the other side of the horizon.
To see the Hubble Space Telescope, yeah. The grass is always greener on the other side of the Earth, is that it?
On the other side of the fence, yeah.
There you go.
Stars are brighter. It's always a pleasure to talk to someone from down under. Mm-hmm. And they allow you to drive them nuts like we've done over the years about what they can see from where they're at.
Mm-hmm.
And what we can see and what we can see mutually. And Orion is something we can both see together.
Yep. Anything on the celestial equator in the sky can be seen from the southern hemisphere and the northern hemisphere. Now, not all of it, depending on how far south you are. So, if you're like right on one of the poles, you're going to see from if you're on the North Pole, you're going to see from the celestial equator north. And if you're on the South Pole, you're going to see from the celestial equator due south. So if half of Orion, for instance, is on the celestial equator, then each pole right on the pole will only get to see half of it. But the farther away from you are from the pole, the more you get to see it. Like we can see some southern constellations down 30, 40 degrees or so below the southern horizon from where we're at. You're a little farther north than me, I think. Not a whole lot, but a little bit.
This reminds me, wasn't New Zealand? It was around this time of the year that New Zealand has their big outdoor, of course it's outdoor, astronomy event. We got to talk to them one time.
Did you? I don't remember.
Yeah, we did. No, we did. We were together on this one.
New Zealand or Australia?
New Zealand.
Was it? I don't remember. I remember the event.
In February, yeah. It was in February, yeah.
They were listening in and stuff like that.
If they happen to be listening in New Zealand, hello.
That would be their summertime.
Yeah, it's a nice event. It's a really good get together for them.
Oh, that's right. Right around that area, that would be about 10, 11 o'clock in the morning, I think, something like that. Let's see. I think
it was a weekend event. That's why I'm mentioning that.
Oh yeah. So it would have been like Saturday morning for them.
Yeah, it's a full weekend event. And somehow we were tuned in.
Glenn was asking a question: how far up is the orbit of the Hubble Space Telescope? I think that's what Nick just put some answers in for him. I just thinking offhand, it's like about 350 miles up, something like that. So, kind of. Let's see, the space shuttle was able to get there, but it was like right on the edge of what the space shuttle...
Right on the edge of its ability,
could get out to. It's as far away from the Earth as it could get. So, there we go.
Which surprised me, because I thought the space shuttle was a lot higher than what it is.
Yeah, it usually hovers around like the space station.
It's high enough that I'd like to get up there.
250 miles or so. Okay, there it is in the information. At its closest to the Earth, it was 334 miles above the surface, and at its farthest from the Earth, it was 336 miles above the surface of the Earth, or I should say it is. That gives you an idea. But that's not high enough for actually us to see it here where we're at. It's below the horizon for us all times. Never seen the...
I'd say Hubble's one of my favorite telescopes out there.
I think so too. Yes, but
every day I check to see what the Hubble's doing.
Mm-hmm. I like some of the other ones too, the Chandra and Swift.
A lot of people use the Hubble and Swift in combination.
Mm-hmm. And sometimes they'll throw some Chandras in there too, like imaging the center of the Milky Way galaxy, close to the black hole in the middle of the galaxy. That too. I like those images combined together. Let's see what else we got.
I'm going to dig out a link here while you're talking.
Okay, go ahead. This
is for Hubble Space Telescope, and it's what it does every day and what missions are up. The reason why I check the Hubble Space Telescope every day is some days there's a mission called a TOO, Target of Opportunity. And one of the missions on the list will get bumped in order to take advantage of the Target of Opportunity. Mm-hmm. And the last time I've caught a Target of Opportunity was Christmas Day.
Oh, was it?
I just happened to be looking at Christmas Day, and the galaxy, I didn't understand which one it was. It had a different name for it, MK101. We know where Galaxy 101 is, but this had a different number.
Okay.
And they were looking at the black hole there, so I was assuming there was something to do with gravity waves. Okay. So when they take targets of opportunities, it's usually in conjunction with the gravity wave surveys, where everybody's turning their
something that like flares up with gamma rays.
This was a black hole doing something, but no one else has reported on it since.
So usually, when they detect it detect gamma rays in part of the sky. Then they turn the optical telescopes in that same spot and see if they can, see a light, a visible light occurrence in that same area too. So they want to know what type of, gamma rays is a type of light, just very high energized. So they want to get an idea, is the thing also producing X-rays? Is it also producing visible light? Is it also producing infrared or radio waves too? So they kind of want to get an idea of all the light waves.
Multi-messenger surveys, they call them. Yeah.
Okay, sounds familiar.
Everybody on board. Multi-messenger, yeah. I love this new age of gravity wave astronomy.
Mm-hmm.
It really brings the package together. Data is a big requirement of astronomy now too. Statistics.
Mm-hmm. It kind of what makes the astronomers go, we saw this event, but we didn't see it in all frequencies. What's going on? Oh, that changes the parameters of how they understand the activity going in these things. Or if there's a delay between one frequency and another frequency, again, it makes them go, now we have some data that we can, redefine our models of how we think this type of system works, whether it is. So there's a lot of that too. So the more stuff they collect, more information they get, the better it's understood.
One thing about the Hubble missions, these reports, I posted a link, and we'll have so you can put that on your Facebook page too.
Okay.
Is you can read these reports. They are written in English, and they're just written in clearness.
Everyday language?
Yeah, they're not heavily languaged up dealing with the subject, which is fine on its own. And a lot of these reports deal with legacy surveys to catch up on all the possibilities they could get out of Hubble before the James Webb comes online. Mm-hmm. Once James Webb comes on, Hubble's still going to be busier, just as busy then as it is now, right? But Hubble started a lot of programs, and Hubble would like to be, a lot of people who've worked through the Hubble systems for the years would like to complete some of these survey missions. And when they pass these survey missions on, Hubble will have completed all they could possibly complete. And now they can pass it forward to the Webb system, because the Webb will just be able to take over from there. Mm-hmm. So they want to catch up on all the possible surveys that they could complete that they've had building over the years. So you'll come across a lot of these requests for satellite time, and you'll see why they get it.
Mm-hmm.
And it brings a subject about what they're doing. I wish there was a more detailed website that talked to exactly what Hubble was doing, as in all the survey systems together and how they interrelate.
Mm-hmm.
And this legacy mission, it's a really nice piece of science that, somebody could build something on.
Mm-hmm. That's what I wish too. I've gone to some of the NASA website articles and stuff like that, and I don't know if they're just kind of buried or they kind of, hog them for the professional astronomers and keep them in the professional journals. But I would really like sometimes more detail in the NASA articles on a subject, and they gloss it over like a newscast, and they act like they don't know what they're talking about, or they think their audience doesn't know what they're talking about.
Well, they should be reading these subjects here. They should be reading these abstracts. Hubble.
So more detail.
And they got to learn how to communicate the subject, I guess.
Yeah, that would be nice. Well, that's what we're here for, too. We do our best. But yeah,
in the language of astrophysics, it's really clean.
Mm-hmm. It's nice.
It's nice. It's clean.
Mm-hmm. Makes it more understandable, more comprehensible. So I'd say more at a medium level of astronomy understanding stuff. I think I told you I'm reading a book about Werner Heisenberg.
Yeah.
It's like his life story. So they're going along about him, and then all of a sudden they're starting to throw quantum mechanics in there. And using quantum mechanics terms like people are already familiar with it. So it's like quantum mechanics scientists are reading about his life, but not the general public.
Heisenberg was on the German side.
Mm-hmm.
Okay, so when it comes to the history of quantum mechanics and that generation, there's a lot of hard feelings. Straight up, there's a lot of hard feelings. This quantum mechanics comes in bits and pieces through as a subject in itself, but the period that covers Heisenberg, like the 30s and the 40s, okay, the heyday of quantum mechanics, he was amazing. Dirac, I just read something about Paul Dirac. Dirac worked with them too, right?
I don't remember.
Yeah, no, Dirac's amazing.
Didn't sound familiar.
Oh, there's Dirac, Schrodinger.
Yep, Schrodinger
is the other one. Niels Bohr is like the godfather.
Okay? There's
Niels Bohr and Heisenberg.
And Born
Heisenberg.
also.
Right. Niels Bohr is Jewish.
Okay.
And the Nazis didn't take him when they took Copenhagen. They let him because he was already a Nobel Prize winner.
Okay.
And they really did want the embarrassment.
Right?
I'm trying to gently work through this subject, guys, okay? Without tossing rocks and hurting feelings here. So there's a play called Copenhagen where Niels Bohr and Heisenberg, who he treats like his son, go for a walk. The walk doesn't last very long. They come back. They never talk again for years. Okay? Now you try, and from this play, it's called Copenhagen, you try to figure out what went on in conversation between those two gentlemen. It's the relationship is like a father and a son, and it's just it tears at you. It tears at you as a human being. They talked about the nuclear weapons, and it looks like Bohr found out Heisenberg was asking him, pumping him for information about it, how much it would take for process to make the bomb. And they're talking about the bomb. And anyway, Bohr says you shouldn't even be working on it, period. And he said, we're just using it for power, for nuclear generation, for electricity. But he knows the questions are related to a weapon. This is when everything starts to really pick up pace on all sides to get this weapon built. The humans involved, it's just, there's a lot of people involved, and it just, if you were Jewish, you weren't even allowed to work in the institutions. Heisenberg, being German, he rose to the cream of the crop. But he said he never worked for the Nazis. He wouldn't build them the bomb. And at the end, you can see he wasn't building a bomb. He had his numbers wrong to begin with. But the field never forgave him. Though Dirac later on in the 50s did point out that he is given credit to Heisenberg for quantum field theory, especially when he come up with that matrix mechanics. But there's at least Mittner's in there. It's an amazing story, amazing human beings. It's just a very tragic period in human history. I'm obviously not prepared to really get the essence of what I would really want to get out. And I worry about tripping over something and misrepresenting and hurting people's feelings, because it's a terrible thing, because these wars were just terrible on sciences. In the First World War and the Second World War. Just devastated the sciences and young people and humanity in general.
I think I'm still reading the period of late 20s, not quite to the early 30s yet, somewhere around that area, maybe into the early 30s. That's where I'm going. So, fortunately, I've read some other stuff about quantum mechanics. Quantum mechanics means how things work when they're really, really small, like atom size or smaller than atom stuff. Quantum means a really tiny amount, and how the atoms work and how they're shaped and stuff like that. They didn't know what the atom, how it functioned, how it worked, what was its shape, what was it made out of, and stuff like that. So they had some clues. For instance, using looking at spectra. Basically breaking light up into different frequencies. And if you take a glass tube of a gas like hydrogen, charge it with electricity, it gives off a light. Now, if you put a diffraction grating in front of it, you'll see different bright bands. So it doesn't light up like a rainbow. Only select wavelengths of the rainbow will show up. Yep, of lines. And so they're trying to figure out what makes these lines. And then they notice too that, well, sometimes the lines are a little double. There'd be subsets of lines and things like that. So they were trying to figure out how could this atom actually work to make these lines in a gas like that. And that was a big thing. Discussion.
Oh, awesome reading, Marty. Yeah, you're right on. That's it.
A lot of math. They had to do it mathematically. There was kind of a conflict between like the experimentalists, guys that were working with the gases and the spectrum and stuff like that, and then the theorists and mathematicians that were trying to figure out mathematically how the atom could possibly do this stuff.
Black body spectrum problems started coming in. Yeah.
And Einstein was a little bit, Heisenberg wanted to talk to Einstein about this stuff. And the idea, one originally was like the electron would orbit around the atom, but Einstein insisted the electron being a particle could not go the speed of light. So that kind of threw a monkey wrench in some of their ideas. It was like, well, the thing can't orbit at the speed of light. It's impossible. It would have infinite energy. It did that. If it did that, so that's impossible. So they tried to figure out, well, how could this thing move fast, and do what it's doing, but not exceed the speed of light, and all kind of arguments like that. So it went really back and forth. As you mentioned, matrix mechanics, because instead of being a point particle, it's a pair of coordinates. Yeah, and the matrices can handle coordinate systems like that. Which the spectrum can only come in quantas, discrete energy levels. And then Niels Bohr started it, and that's where Niels Bohr came in with the atom. So the argument between waves and particles was another thing too. So somebody'd have an awesome theory about particles. Okay, if this was a particle, it would do this. We got all the math right. It has to be particles. But then somebody else would throw, well, wait a minute. That particle can't act like a wave then. How do you explain
particle equation? Yeah.
How do you explain the wave particle? I mean, the wave idea that we're seeing out of these atoms, the light's coming out also in waves, not just particles, and your math doesn't cover that too. I think Schrodinger was a wave guy. He really had a whole bunch of math for waves, and then
he didn't like quantum mechanics.
Heisenberg pointed out, like, well, okay, waves are fine, but it doesn't solve these other issues of a particle that acts like a particle. So they kind of went, now we got to figure it out some more. So,
I know that sounds funny. Schrodinger didn't like quantum mechanics. I wish I never did that.
So a lot of back and forth between different scientists that would promote different theories and the different math, and somebody come up with a paper.
They were both right.
Yeah, they were like semi all right. They were combining, papers together and ripping apart, arguing back and forth. Oh, my way is right, your way is wrong, blah, blah, blah. So
now we got the particle wave duality.
Which I've got to read more on, so let's see what they say. Oh, we're a little bit past our half.
That sounds like a great read, Marty. Yeah,
it is. Fortunately, I've known a little bit about quantum mechanics and some of the terminology, so some of it I'm familiar with. So I'm thinking I may be about 20% ahead of, a non-scientist type of person.
The hard part about it is you're getting quantum mechanics before you get in particle physics. No, this is the way we discovered it. Not we. I wasn't old enough. We stuff going. It's how the subject come about. They found quantum mechanics before they were ready for it, and they found like the particle quantum mechanics, and they found the wave quantum mechanics. That's the two of them, right? One's relativistic, one's non-relativistic. We're lucky to find both of them. Well, they weren't found together, but like we were just discussing, one first, then the other, then both of them together.
So I say, then the author is kind of throwing out these quantum mechanic terms, like somebody that knows the subject would know these terms, but some of the things I've heard of, but I don't know what he's talking about. And then he'll throw things out there that maybe I recognize the wording, but I don't have no clue what it's about. So it's a little bit of a slow read, and it's going to take me a while, and I'm going to have to go back and read some more. Hopefully,
there's some wonderful sites on YouTube.
Okay.
Yeah.
And pick out some stuff that'll explain this to me some more. So, but I'll read through the whole thing first, and maybe it's one of those thick books, so you can kind of reread it again. Let's do a little station identification. You are listening to the Event Horizon here on Astronomy.FM radio. It is Friday evening. This one happens to be February the 2nd, 2018. I got 9:35 in the evening for me, my local time here in the eastern portion of North America. So universal time, that would put it at 2:35 Saturday morning, February the 3rd, 2018. Halfway through our program or so. So we still got another half hour of live broadcasting. If you want to join us in our chat room, please feel to come on over and log in and ask us questions if you want to. Different chat name. It's now called, you can type in chat.astronomy.fm, and that'll get you here. That's different from the old one, which used to be astronomy.fm/chat, but no, it's different. Put chat first now to get into our chat room. That'll get you to the login page. Just type in a name, forget the password, hit login, and you'll be here. So if you've got a question for us, just type it in there. Feel free. We're reading the chat room as we go along here, and more than happy to answer your questions for them. Don't forget, we'll repeat this program every 4 hours for the next 24 hours with a few programs in between. In fact, we have one new program tonight. I can't remember what it is, but a brand new program that you can listen into between the hours. But you can get the whole 24 hours to catch them all again. Let's see. Did Nick miss any links? I don't think so. I think they're all there. We've mostly been talking away instead of putting links in right now. So
we're having a conversation about the conversation tonight.
Yeah.
Well, that's where the subject was discovered, too. Even when you get to gravity, right? Then you get to general relativity, and then you move on to string theory. Then you're back to superconformal field theory. And now you're in ADS space. It really builds on itself. It's not a subject you can just jump in. You really need to go back and say, hello, his name is Galileo. You go talk to Galileo for a second. It's really simple. It is. Go back and say hello to Galileo, what he was up to. He was talking with those rest of those big heads. See, they would all walk around the big head. They'd all dressed up in their bed sheets and go for a walk on a warm summer's eve and go, hey, big head, why does that leaf flutter to the ground? And the big head would just make up the answer. You go, well, because it's got floating qualities and it's got falling qualities. And it's got equal amount, but it's got a little more falling qualities, and that's why it goes to the ground. So they would describe behaviors in nature they would see. And it was description of these behaviors. Well, what happens when what about the behavior when I throw a stick in the water? Why does it float on water? Right? Why does this stick sink after it's been sitting in the water? And the big head would go, if you keep asking those questions, I'm going to throw you in the water. Just take my answers. Heavy things fall faster than light things. And Galileo go, well, no, you're wrong. And the key with what Galileo got onto was when he made this inclined plane and he let this little ball roll down, or a big ball or whatever, he just let it roll. And after 1 Galileo second, because Galileo had to come up with seconds, right? And he had to come up with lengths. And after 1 Galileo second, it moved 1 Galileo distance. Then he let it go for 2 Galileo seconds. And he realized it went, in the second Galileo went 4. And he let it go 3, and it went 9. And it was like a mathematical equation. And that's what Galileo did. He put observation and measurement of behaviors, and he made predictions how energy and matter moved in a coordinate system. Okay? I call it the high five of science. I draw it on my hand. But what Galileo did, he put observation and measurement together instead of observation and making an answer up. And the observation about a behavior that you could make a prediction about based on a measurement.
And math.
And you could mathematically make a prediction that the ball would roll down X amount of lengths and X amount of distance and X amount of time, and it would be there, and it worked. And it was the first time math and a measurement, a line, got put together to make a prediction. And science, that's what science is. It was the birth of science, the observation and measurement of behaviors in nature. And it was like, wow. So then when Newton comes along, okay, he's already got Galileo's system for observation and measurement. Galileo comes up with a system called kinematics. Newton comes up with a system for how stuff moves, and he calls it dynamics. And then he took the dynamics and kinematics, see, big word, but it's only Galileo, and he put them together, and he came up with mechanics. So he had classical mechanics, how stuff moves in nature, whether it's water or rock, a star. And I jumped past Kepler. Kepler's in between. We don't give him enough, right? And anyway, how planets move. So when you took those three subjects together, Newton got it for free. Galileo had to come up with how planets move. Newton got it. He got it for free because it had already been figured out by him. They move on ellipses, right? And then Einstein comes along and goes, I like your dynamics and your kinematics put together, but when I use Maxwell's equations, something breaks down. And what he figured out is the way you do these observation measurements, it always depended on whether you're in an inertial frame of reference or a non-inertial frame of reference.
Whether you're moving or not.
Yeah. And he knew the laws of physics had to be the same forwards and backwards, and he found a way to put them together with space and time. And what he had to do was change space and time. And change the inertial reference frame. And that's how the subject keeps building on from there. And you can, once you get to Einstein doing this special relativity, you got to talk to Lorentz too. The subject becomes easier to handle and easier to catch on to. So now I'm up to about the 1920s, right? 1915 if I want to go to 16 if I want to go to GR. General relativity is just a different animal unto itself. Okay. You don't have to jump into general relativity. You should go back and see Galileo first. Have some fun with Pythagoras and them too. And as you come forward, pick up a little bit of the math history. But you got to do this history because the subject doesn't fall one after the other. Once you hit about the 1910s, it starts branching off. You got these quantum physicists going one way. You got the relativists going the other way. General relativity, like in the 1950s, was a done subject. You know that? There was nothing. There was nothing else for it to do. Right. The last thing they had done was the stars, but then you got these John Wheelers and them got started in it, and then he got the Kip Thornes going, and he got the Richard Feynmans. You heard of Feynman, right? And that's where all this black hole stuff. Not Feynman wasn't black hole stuff. Feynman's was quantum field theory.
Okay.
But the rest of them took the general relativity and ran with it, and turned it into a really cool subject through the 60s and the 70s. And realized how they could attach it to astronomy with these black holes and try to do these black hole measurements in order to observe them and find a way to measure them. And now today we've got it with gravity wave astronomy. But that's the only thing they could dig out of general relativity at the time for it to be of any. It was such a hard subject to measure because you needed such heavy objects.
Yep. And you had better measuring equipment.
Yeah, you couldn't do a GR experiment in a lab unless you could borrow your neighbor's black hole.
A couple astronomy articles I wanted to get to. Let's see. Okay, we'll put this one into our chat room here. This is about a new discovery challenges popular theory about dwarf galaxies. Let me put this into our chat room. Galaxies have, bigger galaxies usually have little galaxies circling around them. Kind of like, our Milky Way galaxy's got the Large Magellanic Cloud and the Small Magellanic Cloud circling around us, plus a bunch of other little ones, not counting globular clusters, but actual things that are considered to be really small galaxies. Andromeda Galaxy's got a couple of small galaxies circling around. The idea was thought that the small galaxies kind of go around the center of the main galaxy in random directions. Well, they've actually been finding that some dwarf galaxies go around in the same plane.
That was pretty interesting, wasn't it?
Yeah, but not in the same plane as like a spiral galaxy. Is pretty much flat and has a plane, but the dwarf galaxies don't orbit around in the same plane as the spiral itself.
No, but they orbit a plane.
They orbit in a plane, yes,
which is really unexpected because they should be just going every which way.
Should be random, as the galaxies kind of crashed and drew together. They would come in from different directions and spiral around, just kind of go around in different random directions. But they're finding out that the dwarf galaxies have kind of lined themselves up going around the bigger galaxy, and that was kind of an unusual.
I put another link in too to go with your story, Marty.
Oh, great!
The same one. I tried to get at that paper in Science.
Okay.
And it's behind a paywall.
Oh yeah.
So I took some general write-ups on it.
Okay.
At Science Magazine, I got one of theirs, and it's got a video to go with it.
Oh, nice.
So the Milky Way and Andromeda are the same thing, and Centaurus A.
Mm-hmm.
The three of them, all three of them, with these dwarf galaxies going around in planes. Mm-hmm. Yeah, mathematically, you're in the you're beyond theoretical.
Yeah, like, how does this happen? And, we'd think that would be not normal, but the normal is the... So,
however, it could be actually normal. It just got to make it a new category where it's normal, because it's at a smaller scale distance than the minimum size block of space that you can do cosmology on.
Mm-hmm.
I don't know the right numbers, a couple light years across. Okay, anything on that scale, it may not be homogeneous and isotropic, but on large scales, homogeneous and isotropic ISO are the same in every direction, and homogeneous means it's just spread out evenly, more or less.
Homogeneous.
Yeah, and so these dwarf galaxies should be isotropic. They, just any which way but loose. Like Clint Eastwood, remember that movie? Right Turn, Clyde?
Any which way but loose, yeah. Right Turn, Clyde, yeah.
So it turns out they're not, and they're on a flat plane, rotating together. And so it takes cosmological models and goes, okay, that on smaller scales we have more structure. Okay, and so when they say it's homogeneous and isotropic on large scales, yes. On even larger and larger scales, no, it breaks down again. So this homogeneous and isotropic lambda CDM model, cold dark matter model, it's a general model for cosmology. I didn't make the names up, guys. I don't know who made them up. That at a certain scale, between not too small and not too big, is just right. But on smaller scales, and then even smaller scales like individual solar systems, every one of them seems to be different, right? So it's not the same on smaller scales. And so at galaxy scales where it should start to be similar, the same, because galaxies are the same amount of galaxies roughly per square block of space as any other block of space, no matter which way you look. Here on these galaxies, individual galaxy scales, no, there seems to be a structure demand. There's a process that produces structure, independent of the model, which says it should be even and isotropic and smooth and all blended up. I'm glad you found that, because it was locked up, Marty.
I know. A lot more scientific publications seem to be more locked up. We used to be able to pull some. They would print out some like news articles and stuff like that. Some of the bigger, more professional to semi-professional publications, and they seem to be locking them up now. So actually, which kind of going with a lot of thought about de-educating the public. It's like, you really should be.
There's still lots of good stuff, yeah.
Yeah, you really should be getting that stuff out there, though, for the general public, not just hold it within yourselves a little bit more. So,
because during these write-ups, there's a lot more information that I'm skipping over myself, not jumping into my head because, hey, I'm not a cosmologist, that they cover in these articles that are behind the paywall, of course. So when we do the general items like here, they jump onto the general cool stuff, but they may be missing completely what the paper's been discussing.
Yep.
But I don't believe so in this part. I think we've got everything we needed, because the only thing they don't mention is large-scale structure and small-scale structure. But, if I get access to the other paper, they probably mention it.
Yep. And that was about Centaurus A, which is a galaxy in the constellation of Centaurus. Most amateur astronomers, that have been down the southern regions have definitely been able to see this one. It's pretty bright, kind of ball-shaped. It's got a dark band going across it. It's pretty cool. What is this about? They're not even sure how far away it is, 10 to 16 million light years away. And it's a very high radio source. That means most likely, it's got a black hole in the middle of it, and stuff's going into it, and it's emitting a bunch of radio waves, and very peculiar-looking galaxy, but reasonably close and kind of big for us to see. So definitely a favorite of amateur astronomers to look at and image. And the more scopes looking at, Hubble, again, like we said before, Spitzer, and the other frequencies that are looking at you wouldn't even recognize. I didn't even recognize this one picture of the galaxy.
Of Centaurus A?
Yeah.
Yeah, I know, because I'm used to it twisted a little bit or so.
Yeah, basically a ball with a dark line through it. Now it's got
the ribbon there?
Or the jet. Yeah, the jet that shoots out of it was like, when you
highlight. You know why that is because we grew up with small telescopes.
Yep.
That's why. We just grew up with small telescopes and
black and white cameras.
Yeah, so when we get the newer pictures, it's like,
Yep.
Yeah.
So you can kind of change the detail that you want to see. So instead of like a white ball, we've got telescopes that can actually look inside the ball, and the pictures can be modified to highlight the inside of it and ignore the outside white ball, so you can pick up detail that normally can't be seen.
Yeah, like galaxies hidden behind it through the black spots. Yeah. How many times you see galaxies poking through other galaxies with these new scopes?
Yeah.
Those new systems.
I got an article on that actually right now. Galaxy behind a galaxy. And the front galaxy actually magnifies the light of the back galaxy.
Oh, they're nice lenses, aren't they?
Mm-hmm.
Hubble, those Hubble systems we were talking about earlier, I put the links in, we're keep an eye on.
Okay.
They like working at those. They work them a lot. Hubble can really work those gravitational lenses. They call them lenses, not just gravitational lenses, because they refer to them as a lens. These large clusters of galaxies, and Hubble's one of the or a set of the camera systems on Hubble really work these guys really well. Hubble can really take advantage of it, and it's the right size too, I guess, for the job for doing these. And the galaxies that are in behind, they found so when they go back deep, Marty, they found lots and lots of galaxies. Yes, which makes sense, because when you do the cosmology models, the universe was closer in, so they expected more galaxies to be closer around. All these models are going to get stretched beyond more. Why do they have to add more time to the universe next? That'll be fun.
I know, just to study it.
Well, they will. I just say, well, we forgot to add this, or we didn't know this was here to add. Now that we add this in, the universe is older.
There's an article about a really big old galaxy. Let's see, there's light for this thing was emitted a little less than 800 million years after the Big Bang.
How'd they get there so fast?
Yeah. Well, it's because there was a intervening galaxy in front of it, which actually kind of magnified the light behind it. And this is a big galaxy. You don't usually get big galaxies way back that early. This one's got like a mass of 100 billion solar masses. Early universe is mostly small galaxies, and later on the galaxies kind of combined together to make bigger and bigger galaxies. So,
I know, if that had 100 million then, what has it got now?
Yeah, did it pick up more?
It would keep growing and big and eat. Yeah, every galaxy just eats galaxies. Talk about our Milky Way being a carnivore.
Yeah, so if the thing was really close to us, would it be, 10 times bigger, 1,000 times bigger?
Oh, it might be some of these, like the great attractors. That's what these things could turn into, like this great attractor that all our galaxies are heading towards.
In Virgo.
Yeah, that thing, or the other one, it'd be in behind the zone, the zone of avoidance. But the Milky Way's got in behind the Milky Way, I guess, is a zone of avoidance.
Not that familiar with it.
Yeah, well, there's the center of the Milky Way there. You can't see past it. So they call it the zone of avoidance. So you avoid that area because you can't see behind it. But we seem to be heading in the direction of a zone of avoidance.
Ah, okay, I get you now.
Yeah, all of this, like we're heading towards the Great Attractor, and even the Great Attractor is heading towards that.
So we're kind of like in the trunk of the car.
Yeah, I don't know where we could go.
We can't see in front of us.
Going, yeah. If we could get going, I don't even know where we'd get to. We're all being dragged in one direction.
Uh-huh.
Another thing I wanted to try to mention today was star lift, and this effect called star lifting. Star
lifting, okay.
Where they take mass off a star. Okay. So if our star ever started to grow too big, that's in millions of years, they'd be able to lift mass off the star, cool it down.
Okay.
And control it. And it's not super advanced technology.
Okay.
No magic weapons.
Okay.
No tech. Yeah.
How do they figure
star lifting?
How do they figure
it's part of the Dyson system. Dyson spheres?
Okay.
You can actually lift mass off the star. They can there's 3 different ways, I guess. I'm trying to pick at it here for the last little bit. The only one I seem to remember is the Huff and Puff system.
Well, that requires building a big structure around the sun to take mass off it. I guess you could
using mercury.
Let's say if you could, build a big enough structure around something, you could also maybe move something fairly large, like a planet, put it in a atmospheric dipping orbit to the sun, and basically, highly
That's
elliptical.
what all the system's about. Yeah.
Dip into the atmosphere of the sun, pull some stuff out of it, back out into space, go back around, dip in, pull some material out of it. Kind of like a twin star system, binary system, it's called.
And then there was about these stars eating their planets.
Yep.
Yeah, because they've been getting these readings from stars that go, wait, it's got way too much lithium in it.
Mm-hmm.
Okay, and they're twin binaries, and yet the stars don't add up, and yet they are twin binaries. And the conclusion is, one of them ate its planets.
Probably one of those super hot super Jupiters. A really big planet that's orbiting really close to a star. Yep. And it's
because the gas giant would have had to collect the stuff further out and come back in and bring it in.
Mm-hmm.
The material wouldn't have been available around the sun to fall in, so it would have eaten a gas giant that made its way back into the solar system, or in toward the sun. Neat finds. Wow. Yep. Astronomy, it's never boring.
Since we're talking about binary stars, we've got a couple of novas reported. Here's one from, they're both from the AAVSO. It's the alert notice number 612. A nova in Scorpius, the Scorpion. Not really bright, about 11th magnitude. So, you'll have to photograph it if you want to image this one. It's thought to be what they called it, a classical Fe, which is iron, doubly ionized iron nova. Basically, you got a white dwarf and another star nearby it. It's pulling stuff off the white dwarf's pulling stuff out of the atmosphere of the star nearby and bringing it down the surface, and it builds up enough material where basically the stuff kind of ignites, it fuses, and makes the white dwarf brighter for a while. And they could tell by the spectrum of the light coming out of the system what's happening in the system. They said there's 2 types of novas like that. One involves hydrogen and nitrogen.
Hypernova?
Yep. No, not a hypernova. Just hydrogen and nitrogen are the main spectrum that they detect out of it, and the other one is ionized hydrogen that they detect out of it. So it kind of gives them an idea of what's going on there. I got another one here. Another one that was in Scorpius. We're about out of time. We've gone through a whole hour. Appreciate you being here, John.
And, pleasure. It's always a pleasure to come and say hello.
Happy to have you here again next week, so we'll do this again. I want to thank everybody that's been in our chat room tonight. Really appreciate you all being in here and everybody listening in. Don't forget, we're going to repeat this program and more programs every 4 hours for the next 24 hours. So keep listening in, and you'll get some more stuff. And then we'll see you all again next week. All right, everybody. Appreciate you all listening in. We're out of here. Thanks all. Good night.
Good night.
We hope that you've enjoyed this program from AFM Radio, the broadcast service of Astronomy.FM. This program has been released under Creative Commons license. Please contact us for details. You may find more of our AFM original programs on our website. It's really easy to find us. We are Astronomy.FM. You may also find us in the iTunes radio listings near the top of the News Talk section, and also as an iTunes podcast selection. We'd love to hear your comments. Please email us at radio@astronomy.fm. Thanks so much for being part of the voice of astronomy around the world and across the known universe. This is Astronomy.FM Radio.
Hi, this is Tavi Greiner, Astronomy.FM's Vice President of Communications. If you enjoy our programming, please let us know with a donation to Astronomy.FM/donate. We really do rely on your support, and it's true, every little bit counts.
AFM.
There I was, doing my thing, and all of a sudden, wham! Astronomy right between the eyes.